This lecture we're going to talk about Airy's stress function. This is a potential function technique for determining stress fields. We're going to describe some examples of Airy's stress function. It's a fairly useful technique, and if you're familiar with Airy's stress functions for a variety of problems, it's kind of a compact way to be able to get stress fields out of a particular situation. All right, well, last time for 2D elasticity, and I really want to emphasize this, that Airy's stress function is for 2D elasticity problems. We saw that we had del squared sigma x plus sigma y is equal to 0. And at this point, we're also going to just neglect body forces. I know last time we said they could be constant, but if they were 0, we'd still get the same equation as we have now. And for now, we're going to neglect body forces. Now, there is a way to incorporate body forces into Airy's stress functions. Most of the problems that we're going to work as examples won't have that need. And we might do an example a little bit later on that goes through one that does have body forces. For now, we're just going to straight up neglect body forces. Well, if that's the case, then our equilibrium equations can be reduced a little bit. So the partial of sigma x with respect to x plus the partial of tau xy with respect to y is equal to 0. And then we have the partial of tau xy with respect to x plus the partial of sigma y with respect to y is equal to 0. Now, there's something kind of interesting when we look at these equations. In a way, they're kind of connected. Right? So here we have the partial derivative of tau xy with respect to y in one equation. We have the partial derivative of tau xy with respect to x in another equation. But even beyond that connection, there's a very obvious connection between sigma x and sigma y, or at least sigma x and tau xy. At least we can write the partial of sigma x with respect to x is equal to minus the partial derivative of tau xy with respect to y. And on this one, we can say that the partial derivative of sigma y with respect to x is equal to minus partial derivative of tau xy with respect to x. Oop, I got an x in the wrong spot. Partial of sigma y with respect to y is equal to minus the partial derivative of tau xy with respect to x. Alright, so I'm going to call this equation 1, and I'm going to call this equation 2. Now, just looking at 1, this connection between sigma x and tau xy implies there's a connection, a potential function. And I'm going to call that potential function phi. It's a potential function of x and y. Remember, we're in 2 dimensions. That we have a potential function where these stresses are derivable from that potential function. So sigma x would be the partial derivative of phi with respect to y, and minus tau xy would be equal to the partial derivative of that same function with respect to x. Another place where you often see potential functions is in potential flow in fluid mechanics. Same sort of reasoning here. Now, if this is unfamiliar with you, I would recommend that you go back and look at a basic calculus textbook for 2D calculus problems. It's usually, if I remember right, in calculus 3 that you'll often see this. If we look at equation 2, we have the same sort of implication. We can derive sigma y from a potential function. I'll call this one theta, call the previous one phi, so that the partial derivative of that function with respect to x will give us sigma y, and minus tau xy would be derivable from the partial derivative of this potential function theta with respect to y. Let's make a little room. Well, if we look at these sets of equations carefully, you'll see that minus tau xy is equal to the partial derivative of phi with respect to x and a partial derivative of theta with respect to y. So this tells me that the partial derivative of phi with respect to x has to be equal to partial derivative of theta with respect to y. Well, that also means that those two functions are derivable from a potential function. And I'll use the notation that our book does. We're going to use the function f, again in 2D, the function of x and y, such that phi is a partial derivative of f with respect to y, and theta is partial derivative of f with respect to x. Well, we're really not so interested in phi and theta. What we're really interested in is sigma x, sigma y, and tau xy. So the stress, sigma x then, would be the partial of phi with respect to y. It's going to be the second partial derivative of the function f with respect to x twice. With respect to y twice. That is a common mistake that I'll see people do. Okay, you see the partial derivative with respect to y is how we got sigma x. And the second partial of f with respect to y gives us sigma x. If I wanted sigma y, if I knew the function f, I would take the second partial derivative of that with respect to x twice. And then lastly, if I want to find the value for tau xy, remember that has that negative sign thrown in there. It would be negative the second partial derivative of f with respect to x and y. And f is called Airy's stress function. So if we have this function, if we can find this function, determining the stress fields is really easy. We just take partial derivatives. All right, so here's the key points I want you to take out of this. I want you to know these relationships. And I want you to understand that this is for 2D elasticity problems only. It cannot be used for 3D. Now, different books use different symbols for Airy's stress function. And the way I learned it was I used the symbol phi for Airy's stress function, and that's fairly common. So here we just use phi for an intermediate function. Later on, we'll give some examples, and I'll revert back to using phi for my Airy stress function. I'll try to label it very clearly as Airy stress function, but whatever symbol you use for Airy stress function, this is how we determine the plane stress components, sigma x, sigma y, and tau xy. Well, let's take a look at something else that we did previously as well. We looked at combined equilibrium and compatibility. Remember we said del squared sigma x plus sigma y is equal to 0, neglecting any body forces. Well, let's take a look at what this is in terms of Airy's stress function. Sigma x is the second partial of f with respect to y twice, and sigma y is the second partial of f with respect to x twice. Well, there's only one function f, and we have an operator that looks like second partial with respect to y twice plus second partial with respect to x twice. That itself is del squared operating on the function f. And del squared operating on del squared, we use the notation that is del fourth f is equal to 0. And this is known as the bi-harmonic equation. In del squared sigma x plus sigma y, it's the Laplace equation, but that's also known as the harmonic equation. Well, what can we do with that? Well, if you have Airy's stress function and you want to find out whether or not that meets the requirements for equilibrium and compatibility, any Airy stress function that satisfies the equation, the bi-harmonic equation, del fourth f equal to 0, will automatically mean that you have some solution to an elasticity problem. Partial differential equations are hard. I understand that. When Airy's stress function was developed, they understood that too. And so the idea then was to kind of make a list of all the equations that satisfy the bi-harmonic equation. And even if you didn't really know what problem you had in mind, it is some problem in 2D elasticity that was satisfied and solved. You can build up a library of functions f and then figure out what problem you solve later on by looking at a particular stress fields. Okay, we're going to do a couple of examples of this. So let's start out easy. Let's start out simple. Let's look at polynomial functions in rectangular coordinates. So remember we said del fourth f is equal to 0. And that's the same as doing del squared times del squared f equal to 0. Now, expanding this out, we would have second partial of f with respect to x twice, plus the second partial of f with respect to y twice, del squared operating on that. Now, del squared is an operator that looks like this. And so we can algebraically do these manipulations. So we're going to end up with 4 terms. Common mistake I see with students on the bi-harmonic equation is they don't consider all the terms that are in this bi-harmonic. So we have the second partial of f with respect to x twice, the fourth partial of f with respect to x twice. With respect to x 4 times. There we go. We have the fourth partial of f with respect to y 4 times. we're going to have the fourth partial of f with respect to x and y twice. And then we're going to have another term that looks like the fourth partial of f with respect to x and y twice. So we're going to have the fourth partial of f with respect to x 4 times, plus 2 times the mixed fourth partial derivative, twice with respect to x and twice with respect to y, plus the fourth partial f with respect to y 4 times. Okay, so that's the long way of writing this out for the bi-harmonic equation. So we can tell a couple things right off the bat with this. Any solution that is third order or lower in terms of the Airy stress function will satisfy the bi-harmonic equation identically. Alright, so let's go back and take a look at some polynomial functions. Suppose we had an Airy stress function that looked like this. A general polynomial a1 x squared plus a2 xy plus a3 y squared, where a1, 2, and 3 are constants. Now remember, when we go to find our stresses from an Airy stress function, the second partial of f with respect to x twice is sigma x. And in this case, that would be 2a1. The second partial of f with respect to y twice, I've done the wrong thing. Second partial of f with respect to x twice is sigma y. The second partial of f with respect to y twice is sigma x. So if we take the first partial, we're going to get 2a3y. Then we take the second partial, we're going to get 2a3. Okay. And the negative of the second partial of f with respect to x and y is tau xy. And that will just give us the constant a2. Alright, so this would be what our Airy stress function would look like if we had a region of constant stress. So we can sketch this out if we want. We can have a plate, if you will. It's lying in the x and y plane. And everywhere in that plate, we would have the stress, sigma x, being a constant, 2a3. Likewise, in the y direction, the stress would be a constant, 2a1, and the shearing stress these would point these directions for equilibrium. The shearing stress, tau xy, will be a constant, a2. Okay, so that's not a terribly interesting Airy stress function solution. But we sure do know it satisfies combined equilibrium and compatibility for isotropic stress-strain relations, because del fourth F is going to be equal to 0. Well, even though this isn't a terribly interesting Airy stress function, if we're dealing with linear elastic materials, we can use the idea of superposition of stress states to allow us to build up more complicated Airy stress field solutions. Let's take a look at a couple more examples. All right, instead of a quadratic form, let's look at a cubic form. Now this isn't a super general form, but let's just take our area stress function f to be equal to a1 times y cubed. Now remember, if I take the partial derivative of f with respect to y one time, I'm going to get a 3a1y squared. If I take the second partial of f with respect to y again, I'll get a 6a1, and that would be equal to the value of sigma x. Clearly, if we were to go and find the same expressions for sigma y, we would get 0, and tau xy would also be equal to 0. So in this case, it's equal to the second partial of f with respect to x twice, and this one is equal to minus the mixed partial derivative, second partial with respect to x and y. Well, what is 3a1 times y? I need a y right here. What is this solution for sigma x? 6a1y. We do know that it is some sort of solution because if we do del fourth f, the biharmonic, that will equal to 0. Okay? Well, the answer to that question is what stress field does that correspond with? It depends on how we look at something. Look at a region. Okay, let's suppose we have a region that's rectangular, and we put down the middle of this, our coordinate system is our x-axis, and up here is our y-axis. And this would be y is equal to plus c, and down here would be y is equal to minus c. Well, what this equation is telling us is that our stress field in the sigma x direction varies linearly with distance y. So as I increase up the y direction, my stress sigma x increases. As I go down in the negative direction, my stress, well, it increases in magnitude linearly, but the value goes down, becomes more negative. And this is the same everywhere in this particular region. I'm just going to draw it on the ends, but every cross section, every bit of this has the same stress field. It's tension on the top and compression on the bottom. Now the value of this would be minus 6a1c on the bottom and plus 6a1c on the top. Well, now we have to think, well, what problem have we just solved? What problem corresponds to this area stress function? And that problem would be the problem of a beam in pure bending. Now remember, we did the three-dimensional elasticity problem, but now here we have a nice shortcut way to do the two-dimensional elasticity problem with the area stress function. Well, we looked at this region, but let's say we only looked at the top half. Maybe we wanted just to look at a region in which y was always positive. So we put our coordinate system down here. Well, what do we get? Well, we still get a region where the stresses vary linearly with distance. And according to this equation, we get 0 down here. If we say that this is 2c in dimension, then the upper stress level would be 6a1 times 2c. Well, what problem is that? Well, that's a problem with bending and an appropriate amount of tension to get us down to 0 stress down at the bottom. Well, what happens if you don't have 0 stress down at the bottom? Maybe your stress distribution has a non-zero value. Well, what you can do is go back to the previous page and add in a term that accounts for that particular value of constant stress, sigma x on the bottom, and make the adjustments appropriately. All right. Okay, so we looked at two different regions. Well, let's look at a maybe a little bit more interesting region. Maybe our region is a wedge. And we'll go down here at x. This is our y. And this height, again, is going to be 2c. So it looks a whole lot like the previous problem that we worked. The stress distribution on the left edge will go from 0 to the maximum value of 6a1 times 2c. But if we have a wedge at an angle, and just to make this easy, let's do a 45-degree angle, we're going to have a combination of tractions on this slanted surface. Okay, I'm going to have to be careful how I draw this. The tractions will vary from 0 to some value. There will be a shear traction, and there will be a tensile traction. The tractions can be found by our friend, the traction equation. T sub I is equal to sigma ij in j. So again, there's all kinds of things, and you can just, the more clever you are and the more exposure you have to these different kind of stress functions, the more interesting things you can build up. Let's go ahead and find these tractions. Let's go ahead and look a little bit deeper in this problem, and then we'll probably have another video for higher order Airy stress functions. Let's make a little bit of room. All right. So if we are on this particular region, we want the normal vector to that slant, and that normal vector, since it's a 45-degree angle, will look like 1 over the square root of 2, 1 over the square root of 2, and if we, we can put in 0 for the third one if we want. Our stress tensor components, sigma or sigma ij, will look like this. 6a1y, where y is the variable, it changes as y changes, but all the other stress components are 0. All right, now, something that's really important, these two terms, if we do this multiplication, must be expressed in the same coordinate system. Alright, so let's compute our tractions. T sub I is equal to sigma ij in j. If I want the traction vector component 1, that would be sigma 1, 1 in 1 plus sigma 1, 2 in 2 plus sigma 1, 3 in 3. That would be the same as taking this vector and multiplying it by this row. What we would get would be 6a1y times 1 over the square root of 2, and the other terms being 0. The t1 would be the same as the traction vector component in the x direction. T2 is equal to 0, and T3 would be equal to 0. Alright, now this t in the x direction, that's the traction in the x direction. What we'd really like to have, instead of the traction in the x direction, remember that goes this way, at every point up this incline. What we'd really like to have instead would be some tractions in the direction normal and parallel to the inclined plane. Okay, so for example, if I want the traction normal to the inclined plane, I'm going to take this vector for t and dot it with n. Now there's only one non-zero component, and so this reduces down to tx that I just have times 1 over the square root of 2. Now tx is equal to 6a1y times 1 over the square root of 2. Then I have another square root of 2 then from here, and so that's going to end up being 6 over 2, which is 3a1y. If I want the traction component tangent to the inclined plane, I can go through a similar process, and in this particular case, since it's in 2 dimensions, it'll be the same thing as taking my t well, we can complete the Pythagorean theorem. It's probably the best way to say that. We can complete the Pythagorean theorem. We can find out what that traction vector component is. That would also be equal to, in this particular case, 3a1y. Alright, well, let's take a break on this one, and we will pick up with some higher order Airy stress functions on the next one.